Welcome, Simon. Please take it away.
Thank you very much. Good morning, everybody. Thank you much for joining me. So the topic of this talk is really a summary of all of the work I did towards the end of last year around rewriting some code I'd built a number of years prior to that, which helps you essentially reverse engineer component diagrams from Java apps. So that's the premise here. So quick background before we jump into this. Architecture diagrams historically been terrible. I'm sure you see many of these sorts of architecture diagrams kicking around your own organizations. Not many people want to use UML these days for a whole bunch of mythical reasons. Most of these things are just excuses, of course. And many people just want to use boxes and arrows. So the premise of all of the work I've been doing around diagramming over the past 10, 15 plus years is really that's fine. Boxes and lines are fine, but make sure you have some degree of structure and the notation you use is self-describing. That's really the principle underlines my C4 model. So a quick show of hands, who's using C4 here? Is that a good chunk of you? About half or so. Cool. So hopefully I'll introduce C4 to a bunch of other people here who have not seen it before. In order to understand all the stuff we're going to talk about today, I need to briefly introduce C4. C4 is essentially two things. It's a set of hierarchical abstractions and a set of hierarchical diagram types that map onto those abstractions. So this is the set of abstractions that sits behind C4. The biggest of these is what I'm going to call a software system. A software system is typically something that a single team is building, has ownership of, can see the internal implementation details of. If you zoom into the boundaries of a software system, I'm going to say it's made up of one or more containers. By container, I mean application or data store, and we'll see some examples of that shortly. Zoom into the boundaries of an application, and it's made up of components. So that's specifically what this talk is about today, and components are built from code. So that's the four set of abstractions that underlies C4. C4 is actually named after the diagram types. So it's context, containers, components, and code. So yeah, it's four levels of diagrams that map onto those four levels of abstraction. And really we draw a system context diagram. This is the top level diagram. It shows you the system and the world around it. We then do the Google Maps pinch to zoom. We do the Google Maps pinch to zoom on the software system box, and we open that up, we show the containers inside it. We choose a container, zoom in, show components, choose a component, zoom in, show code. So the concept here is diagrams as maps. So I live in Jersey in the Channel Islands. If you do a search for Jersey on Google Maps, you'll get this picture here. That's the one I'm trying to point. I can't reach. That picture there. This is great if you want to know where the airport is and how to get from the airport to the main town. If you've never heard of Jersey before because you've not seen Bergerac, this is too much information. So how do you fix this? You pinch to zoom out. Jersey's a tiny island, so once you pinch out far enough, it disappears. On the flip side, you can zoom in and zoom in and zoom in. And I wanted to do the same thing with architecture diagrams, essentially. So that's the summary of C4. For those of you who have not seen the C4 model before, that's essentially the summary. It's a set of hierarchical abstractions, a set of hierarchical diagram types. It's a notation independent. You can use any notation provided it's described with the diagram key. And therefore, by definition, of course, it's tooling independent. So I'm going to do a bunch of narrative and some demos on top of the good old Spring Pet Clinic sample application produced by the Spring team. And I'm going to show you how I'm going to utilize this a little bit later. So the system context diagram in C4, in order to draw that, you have to ask these questions. So what's the scope of the thing we're building? What features sit inside it? And how does it fit into the world around it in terms of people and software systems? Answer those questions and you can draft up a system context diagram for any system that you are interested in. So this is my example diagram to describe the Spring Pet Clinic system. So this box here is the system. That's the thing produced by the Spring team. And if you dig around the code and you dig around the documentation and the presentations, basically there's this one type of user. It's an employee of this mythical clinic, and they use the Spring Pet Clinic system to do a bunch of stuff. So that's my system context diagram. It's showing you the context around the Spring Pet Clinic system. Pinch to zoom, drop down to level 2, draw the container diagram. The container diagram is a different set of questions. So what are the major technology building blocks? What are their responsibilities? And how do they talk to one another? This is my container diagram I've drafted up for the Spring Pet Clinic system. So we still need our clinic employee. We're telling the same story at a lower level of detail. And this is how I think the Spring Pet Clinic system looks from an architecture perspective at the C2 container level. So there is a Spring Boot web application. That's the thing we're going to decompose later, talking to a relational database schema. All good so far? Perfect. So let's backtrack a second. Can we automatically generate the two diagrams that I have just presented to you? So can we automatically generate a system context diagram? No. So the system context diagram was the user talking to the software system. That information is not easy to get from the code base. If I just give you the code and ask you to draw a context diagram, you're going to need to have some knowledge and do some work to find that out. So the system context level is hard to generate. What about the container level showing applications and data stores? Can we generate this automatically from the code base? Potentially, but it's not particularly straightforward. So if we look through the code base, you'll find the Spring Boot application entry point. This is the public static void main method with the annotations. So that corresponds to the web application box. Right, so that's kind of nice. And if you look through the GitHub repo, you can find some references to things like database schemas. And that corresponds to the relational database schema container on the container diagram. So in theory, you could write some code or some tooling to reverse engineer your repository or your source code tree. You could find these types of things and generate a diagram. Possible, but a little bit tricky. So the issue here, of course, is there's not enough machine readable metadata in the code base to automatically generate levels 1 and 2. That's essentially the problem here. What about the component diagram though? So once we zoom into that web application box, what about the component diagram? So what is the component diagram showing? It's showing the major structural building blocks inside that application, the responsibilities and how they relate to one another. What do we mean by component here? So my definition of component is kind of based on the UML definition of component, but I want a little bit more precision around it. So this is what UML says: a modular unit with well-defined interfaces, replaceable within its environment. That's kind of all fine. I'm going to say this: a component is a modular unit, so it's a grouping of code. It has a well-defined interface. It is replaceable. Insert Liskov substitutability, and it resides inside a C4 container. So again, I'm going back to the predefined levels of abstraction here. So that's what I mean by component. So can we automatically generate a component diagram by pointing some tooling at a Java code base? The issue here, the complication here, is that when you do that, most tools don't see components, they see raw code. Classes, interfaces, enums, packages. So if you point, in this case, this was IntelliJ idea, and say reverse engineer this code base, it gives you this picture, showing you the 24, 25 classes, interfaces, enums inside this code base. Now this is a sample app and it's relatively small. You could see how this approach would explode given the complexity of most enterprise systems. So that's one example. Here's another example. This is Visual Paradigm. I asked it to reverse engineer the same code base, and it's given me a kind of uglier version of the same picture, essentially, with lots and lots more detail. Apply this technique to your enterprise apps, you're going to get hundreds and hundreds of thousands of boxes. So what about doing this on a package by package basis? Well, in this particular example, we've got the Spring Pet Clinic package, and then under that is a vet package, a model package, and an owner package. Is that useful? No, because there's lots of code inside those packages. So just having a package diagram is not particularly useful in most cases. And I'm going to come back to that in most cases statement a little bit later on, because there are some times when that might be a useful diagram to draw. So although the code we write embodies our architectural ideas and principles and intent, right? So all of the decisions we make as developers, designers, and architects end up being implemented as code. They're not explicitly present in the code base. So we need a way to kind of find these things and reverse engineer them back out of our code base. This is what George Fairbanks calls the model code gap in his book. So the model code gap goes like this. we're having an architect discussion about one of your software systems, we're using words like module, component, subsystem, layer, and so on. So we have a whole bunch of words we use to describe architectural constructs and building blocks. The languages we use, in this case Java, does not have those same things as first-class citizens. So I can't type public component X in the Java language. There is no component keyword. There's also no layer keyword in Java. So if I consider my application to be a bunch of components organized into layers, I can't explicitly state that with Java. There's no component and layer keyword. So the model code gap is basically we have this view of our system from a top-down perspective, and we have the code from a bottom-up perspective, and they should meet. We should be able to trace up and down those 4 levels of abstraction cleanly and easily, but they miss at some point. And then we have lots of weird conversations about, well, what do you mean by component? What do you mean by module? And that's what I want to kind of resolve here. So what's the approach? George Fairbanks suggests we adopt an architecturally evident coding style. So this is essentially dropping hints and tips and metadata into the way that we write code, so then it makes the architectural ideas and principles much more evident to whoever's reading the code at a later date. Now that sounds very kind of high level and grand. I completely get that. So what are some examples of an architecturally evident coding style? Naming conventions. So if I've got a bunch of things I consider to be components in my code base, why don't I write those things with component in the name somewhere? So that's a really, really simple example, of course. We could do things with abstract base classes and interfaces. We could implement a component marker interface. We could have all of our components extending an abstract component class that also gives us logging and auditing and all sorts of other stuff. So then we just find all the subclasses and then we have our components. We could mark things with annotations. So Spring does this a lot, of course, if you use Spring Framework, at controller, at repository, at service. So those are architecturally evident coding styles, essentially. Java EE does the same thing, and we can invent our own annotations to demarcate building blocks in our Java code bases. This is probably my favorite, or one of my favorites, packaging conventions. So you have some set of folders representing packages, and then underneath that, every sub-package represents a unique individual component. I tend to call this package by component. I really like this as a way of structuring Java code. If you want to know more about this specific approach, I have a talk I did back in 2018 called Modular Monoliths, and in that I outline various different approaches to structuring Java code. But yeah, I call this package by component, and it tends to end up with really nice, well-structured code bases, and it makes it easy to reverse engineer diagrams of later, of course. Modules. There are different approaches to modules here in Java, aren't there? You've got kind of hard modules or soft modules. By hard modules, I mean things like Maven and Gradle modules with some very hard, well-defined boundaries. From a softer perspective, you've got things like Spring Modulith. So Spring Modulith, if you've not seen it, essentially provides a bunch of conventions that you follow as a developer to demarcate your module boundaries, and it uses tests to enforce that. So one of the kind of issues with Java is there's no proper sub-package concept. All packages are just packages. They're all flat packages, essentially. There's no, oh, this thing is a child of a parent package. That doesn't exist. So Spring Modulith puts some tests around enforcement of that sort of thing. So those are some ideas around architecturally evident coding styles. So what we do now is we basically use those things to go find components in our code base. There is a caveat here, of course. If your code base is a mess, this doesn't work. Unsurprisingly. So if you've got one of those teams which is like 100 developers and everybody's doing something different, good luck. This is not going to work for you. I apologize. I have no answers for you apart from refactor your code base. If you set out with some architectural principles in mind and you said something like, we're going to structure our code as components in layers, these are the layers, this is how we do naming, this is going to work beautifully for you. So with things like Spring, this tends to work better because Spring encourages teams to do things in a certain way. So what I'm going to try to do here is I want to extract as much of the software architecture model from the code as possible, especially at that components level, because that is the level of volatility in most code bases. And I'm going to supplement it where necessary, by which I mean let's manually create the top two levels, context and containers, and then automatically generate the component level. So this is my setup. So I've got a bunch of ways to get context, containers, and code, and I want to fill in that component level. So how do we do that? The added complication here is that we're all using different architecturally evident coding styles. So I might be using naming conventions, you might be using modules, you might be using annotations. So therefore, it's very hard to create a single unique tool that understands everything and the way that all teams are working. Now, I'm sure AI can promise to do that, but I think it's quite hard. So we need to break this down step by step. And the set of steps is going to be the same, but some of the contents of the steps are going to vary depending on your code base. And there are 4 major steps to essentially identifying components in a Java code base. Step 1 is you need to identify components. Now, this is a bit counterintuitive, and I get this, but to reverse engineer a code base, you need to understand it. I think it's very hard to chuck a random code base into a tool, or an AI tool especially, and ask it to generate you a diagram if you don't know what you're expecting to get back. So this whole thing requires some knowledge of the code and how you think it's structured. So what you have to ask yourself is, well, what architectural styles are embodied in the code base, and what sorts of rules and principles and standards and conventions have we adopted as a team, and as hopefully they are all the same. So what I'm trying to basically say is, what components do you expect to see on a component diagram? You have to have an idea of the components you expect to see before you can go through this entire process. And you have 2 options to do this. You can either do top down or bottom up. So from top down, I mean, you look at your code base and you grab a pen and a piece of paper and you sketch out some sort of diagram of what you expect the component diagram to look like when you go through this reverse engineering process. So for the Spring Pet Clinic example, this is broadly speaking what I think the component diagram should look like. So imagine I have some knowledge of this code base, I've been working on this regularly. These are what I consider to be the architectural building blocks, the components I want to see. The other option is to attack this from a bottom-up perspective and start with the code and try and collapse and group things together. So if we go back to my IntelliJ screenshot, this is all the code in the Spring Pet Clinic application. Do I want to show all of these things on my components diagram? No. What have we got here? We've got a bunch of stuff here which is basically just data structures. These data structures are anemic domain classes. There's very little logic in them, and they're used by lots of other things, so they're shared across the code base. So therefore, I don't think they're structurally important from an architecture perspective. Now, some of you are probably going, well, hang on a second, and I agree. If you are doing a fully kind of domain-driven design, ports and adapters, hexagonal style of architecture, your domain concepts are going to be super, super important and very critical. So you do want to leave them in this whole thing. But for this example, they're just anemic data structures, and I don't really care too much about them. At the bottom, we've got a bunch of springy configuration-y things, which are not really important. That's the application entry point. We've got some configuration down here. And we've got this pet validator and pet type formatter, which are just kind of Spring MVC type things. So given this picture, let's ask the question, what can I remove? And the answer is I'm going to remove all the stuff I've just highlighted. So I'm not interested in the anemic domain structures. I'm not interested in the application entry point, and I'm not interested in the Spring configuration and helper classes. That leaves me with the repository classes and the controller classes. So if we remove those things from this diagram, shuffle all the boxes around, we get this, and we can kind of get the same diagram I did from the top-down approach as well. So that's step 1. It's try and figure out what you're expecting to see. This doesn't need to be perfect, but you need to have some sort of first attempt. Step 2, now we've got a bunch of things we want to see. We need to categorize them. Why? Because we need to figure out how to identify the different categories of components a little bit later. So either approach, top down or bottom up, what we can see here is we have essentially a bunch of web controllers and data repositories. again, doesn't matter which of the pictures I generated we use, we've got web controllers and repositories. So we have two categories of components that we essentially want to reverse engineer out of our codebase here. Step 3, we need to identify the rules that we can use to identify all components in those two categories. And there are two steps here. We want to identify the primary type of the component and then potentially any supporting types of that component. I'm not going to talk about supporting types until later because it adds a bit more complexity. For the Spring Pet Clinic example, we only need the primary types. So what is the primary type? The primary type is essentially the unique identifier for the component, expressed in this case, because it makes most sense, as a fully qualified type name. So given the web controllers, that's very straightforward. There's a nice, simple one-to-one mapping between those 6 boxes and classes in the code base. So that's the set of classes we have. That's the set of classes we're looking for. The way to think about this is very simple. Imagine we've got a big list of all of the Java types in that code base and we load it into a relational database. What query would you use to get that subset out? In this case, we've got a couple of options. We can do a select star from types where annotation is controller, at controller, that's the Spring annotation. So that's one way to identify all of those MVC controllers. Or we could say identify all types where the name of the class, the name of the type, ends in the word controller. So we have a couple of different options here to identify that set of web controllers, essentially. So that's nice and straightforward. For the data repositories, those are the 2 data repositories. So what are the rules we need to use to find the repositories? You have a couple of options. There's always a bunch of options here. We could find all extensions or implementations of the repository or JPA repository interfaces. I'm not keen on this way because now we have to look for 2 things. The simpler approach is to find all types where the name ends in the word repository. Right, that's nice and simple. So now we have 2 sets of rules essentially. Once we have a set of rules, we can codify them and we can automate the process to reverse engineer this from the codebase. So it's demo time. What I've done for this demo is I've git cloned the Spring Pet Clinic repo, I've changed directory, and I've built the packaged version of the Spring Boot app via the Maven build. That's all I've done. There's no cheating. The output of this is essentially the Spring Boot WAR file that you use to run the Spring Pet Clinic application. So that's the thing we're going to run all of this stuff on top of. So on my laptop, and I hope it doesn't crash. I mean, my laptop, not the whole thing I'm using here. There's a hardware issue on my Mac, I think. I'm running a copy of Structurizr Lite, which is my open source tooling to help people create architecture diagrams. And this is Structurizr Lite running. This is the multi-workspace version of Structurizr Lite if you are using Lite. This workspace is the diagrams I've already shown you. So this is the context diagram. I can double click and get my container diagram. So we want to be able to double click this web application box and drop down to the component diagram. So how do we do this? Let me show you how this is set up. So this is the Structurizr DSL. So this is my domain-specific language I crafted up a few years ago to help teams model their software architecture. If you've not seen the DSL before, basically what we're doing here is we're defining a workspace, we're defining our model, which is all of our elements, people, software systems, containers, components, relationships, and we're defining our set of views, and the views get mapped onto the diagrams. So in this particular example, we are defining a person. This is the clinic employee. We're defining the Spring Pet Clinic software system. We have the relational database schema inside the software system boundary, and we have the web application container again inside the software system boundary. And we've added a couple of relationships here. So clinic employee to the web app to the relational database. And these things are my 2 views. So that gets you the example diagrams that I just showed you. So what we do now is we go to version 2 of this. And what I've done now inside the web application container is I've added this exclamation mark components part. So this is basically saying, go and find components. So this is using all of the component finder code that's sitting underneath the covers. I'm going to point it at the compiled Spring Pet Clinic application. I'm going to say I'm only interested in looking at code that sits underneath the Pet Clinic package. When you build a Spring Boot application, you get your code and you get a bunch of Spring code. I don't care about that. I just want to focus on my application code. And I have two strategies for identifying components. Strategy number one is to go and find all types that have an annotation of @controller. So that's org Spring Framework stereotype controller. So that's going to get me all of the web controllers. And the second strategy is basically a name suffix matcher. So go find all the types where the name ends with the word repository. So that is it. Using that little block of the Structurizr DSL, we can point it at a pre-built app. We can give it some strategies with various rules that we can configure, and we can get a component diagram. So this is the version 2. Double click to get the container diagram, double click, and this is my component diagram. Welcome controller, crash controller, visit controller, pet controller, owner controller, they have a dependency on the owner repository. So what this does is it finds components, and it also finds the links between the components based upon the dependencies in the code. And there's the vet controller talking to the vet repository. So how is this working? This is using Apache BSL under the covers, and it's basically doing some bytecode engineering reflection stuff. It's finding out all the stuff about the code and the dependencies between the code, and that's what gets you this diagram essentially. So that's version 1 of my component diagram. The picture is missing around this, and there's a bunch more work we need to do here. So how do we take this and do more interesting things with it? Well, first of all, I'm going to filter the crash controller. The crash controller is just used for serving error pages. I don't really care about that too much. So I'm going to filter the crash controller out. How do I do that? What I've done here, this is the same thing. And I've said exclude the crash controller. So I'm just using a regex here to filter out stuff I don't really care too much about. So this is going to get me to this version of the diagram, which no longer has the crash controller. Step 4. I want to connect the components to things that exist outside the application boundary. So what I want here is I want links from my user to my controllers and links from my repositories to my database schema. That's essentially what I want to do here. So I want to create this diagram. So clinic employee to the controllers, controllers to the repositories, repositories to the database. So how do we do that? This is version 4. I've got this little for each thing in here. And basically it runs, the DSL runs this code for every controller component it finds. And it simply says, for each controller component, connect the clinic employee to this, the controller component with a description of users. So that gives me all of those top arrows. And there's a similar thing for the repositories. For each repository, link this to the relational database schema. So that's essentially giving me the top and bottom of the diagrams with all the arrows. So we're getting there now, aren't we? So this is what I'm saying. We have to extract as much as we can from inside the code base and maybe supplement it with the stuff that's a little bit harder to automate. So this is a kind of multi-pronged approach here. So that's version 4, step 4. Step 5 is going to be adding some styling. So I don't like the gray boxes. Let's make them all a nice color. So then we can use our diagram key to figure out which are controllers, which are repositories. How do we do that? This is the version 5 approach. And all I've done is the same thing. So with the Structurizr DSL, any styling is based upon text-based tags, much like you have HTML elements and CSS classes. So inside this for each block, I've said add a Spring NVC controller tag to all of those control components, and similarly add a Spring data repository tag for all of the repository components. And then down here somewhere, I've got the various styles which just target those tags and change the colors. I didn't show you the component diagram definition, but it's just this. So this is the component diagram definition for the web application, and we're saying it includes style, which is include all of the components inside the web application and include the things they link to outside of the application boundary. So that gives us a nice looking diagram. So we're pretty much there. We could run with this and be happy that we have a nice diagram. Every time we add new controllers, new repositories, we change relationships, we rerun this whole process, and you get a different diagram. So this is probably sufficient for most teams, but I want to see how far we can take this and go a little bit further. So what does step 6 bring us? I want to add some descriptions. I'd like to automatically fill in the description boxes with descriptions of what those components mean. So where can we get this data from? Well, it's not in the bytecode. There's nothing in the bytecode aside from runtime retained annotations that can give us any commentary. So we can't use that, but we could use the source code. So if I bring up the source code in IntelliJ, there's an empty java.comment for the controllers. If I was on this team, I'd now be opening a pull request to add some commentary here, and then we could use the content of that java.comment. Thankfully, there is some for the repositories. So someone's gone through the trouble of writing a java.comment. Let's just use that and stick it on the diagram. Now, we don't want to use the whole thing here. We just want to use, say, the first sentence. So let's use that. Let's do the first sentence. And this is what we get. So now we automatically generated the description of that box from the source code. How do we get that working? What we have now is we are saying for every Spring Data repository, the description is the first sentence. And this automatically knows to go and look at the source code, and it uses the Java parser library to go and basically parse the source code and pull out the java.comments. But you're thinking, well, hang on a second. I pointed it at the built version of the app, not the source code. Correct. I've had to do both now. So I need to point it to the bytecode because that gets me the components and the relationships via the dependencies in the bytecode. I also have to point it to the source. Once you point it to the source, this all works beautifully, completely out of the box. You don't need to do anything here. So that's quite nice. So now we have a component diagram with some descriptions, and now we can go into the source code and change the descriptions, rerun this. You get nicer diagrams, of course. So what else can we do? How can we take this a step further? Well, what we could do is we could start adding links to GitHub. So when you double click on a component, it takes you to that component in GitHub. So now what I've done here is I've added some URLs to all of these things, and they're all hyperlinked. And if I double click this, it takes us to the GitHub page for that particular primary type. How is that done? Very simply, there is a new thing on here which says set the URL of all of the components we find, and the URL is essentially a prefix on the source tree of adding that. So we add that URL to the calculated source tree. We have that because we pointed at the source, and now we can basically create a bunch of hyperlinks super simply. So now you have a way to have a component diagram, and you can double click and you can take people to the code. You don't have to hyperlink to GitHub, of course. You can hyperlink to anything you want to. So I think that's pretty cool. I think we have a nice way to automatically reverse engineer a bunch of stuff out of codebase, multiple rules we can apply here, and it's relatively straightforward. There's not much work you need to do here apart from apply the built-in strategies and rules to identify the things that exist in your codebases. So that's my demo. We still have a bunch of time. So I'm going to go back to this primary supporting type thing I kind of skirted around a little bit earlier on. No, I'm not. I'm going to show you one more demo. I'm going to show you one more demo, and then I'm going to talk about primary supporting types. If you have a very large code base with lots of components, some of you might be thinking this approach does not work because you're going to have lots of boxes, lots of arrows. So how do we make that work? I have a talk online on YouTube. It's called C4 Model Misconceptions, Mistakes and Misuses. You can apply the techniques I talk about in that talk to this level of detail as well. So this is what step 8 is all about. So this is my component diagram, and it's showing you all of the components inside that web application boundary. If this was gigantic, you might find that having a single static diagram is not particularly useful. So in my Structurizr Lite tooling, again, this is all open source and free, you click this little explore button and you get this little fancy D3JS force-directed graph. And this is showing exactly the same thing as the other diagram did, but now it's showing you in a much more concise, succinct visualization format. And this is much better for exploring, and the key word here is exploring large code bases. So imagine you have something like this showing all of the components and their dependencies in your code base, and you want to say, give me a list of everything that talks to the owner repository. Easy. So now you can start to look at things like impact of change when you were to change the API, the internal API of something. And there's tooltips, and you can add a whole bunch of metadata behind here. For those of you who are a bit nearer the front, there are some properties that are automatically set on these components that tell you where the source came from and a bunch of other things as well. So there's some additional metadata behind the scenes that you can use for doing other things with later if you want to. So option one is you craft up a kind of more interactive visualization. Option two is rather than having one diagram showing all components, what we could do instead is maybe draw 1, 2, 3, 4, 5 diagrams, each focusing on one controller each. So a slice through the architecture one by one. So we could have slice one, which in this case is the owner controller to the owner repository to the relational database schema. Slice two is the pet controller to the owner repository. Slice three is the vet controller talking to vet repository. You get the picture. You could craft these things by hand if you know the names of them, or you could just write some code to automatically generate these things yourself. So in step 8 here, in version 8 of this example, I have some code somewhere. Where is it? Here. And it basically says, so you can call out to scripts in Groovy, Kotlin, etc. I'm basically saying run this little views.groovy script. This views.groovy script essentially goes and finds the user. So there's a Java API sitting under the covers here. It finds the web application container. It then says for all components, filter them out to be just the controllers. Create a view per controller, add the default elements, and remove elements that you can't get to from that controller. So that gives you the slice, and then we add the user back in because it's the top. So that little bit of code generates you those five diagrams automatically. And of course, because this is code base, you can apply any sort of strategies and structures you want to generate you a whole bunch of diagrams, again, completely automatically, which I think is quite nice. So that's the little demo thing. There is one more thing you could do here. There's a tool called ilograph, which has nothing to do with me, but my Structurizr CLI, the open source command line interface tool, which is again another wrapper on the Structurizr for Java library. It allows you to export your Structurizr workspace into the ilograph format. So that's a CLI command I can run there. If I go here, I have so this is the ilograph YAML format. If I take this is what was created by the export, and I open up a new tab and I go to app.ilograph.com, new diagram, discard that one, type in mine. So this is an ilograph visualization of that same model, and includes the employee, the pet clinic system, the web application, the database schema, and all of those components. So if you have a bigger, more complicated architecture, you could use this type of visualization to really, again, start exploring. And we can start clicking around, and it's interactive, and it shows nearest neighbors. It's a very nice visualization. Again, this tool's nothing to do with me, but I liked it so much that I built an export format to this tooling. So that is the demos done now. I do want to talk briefly about the primary supporting types thing. So primary types. There's a bunch of different ways you can identify primary types, and again, this is based upon all those architecturally of encoding styles I showed you before. So if you have annotations, there's an annotations matcher. If you are extending a base class, you can use the extends type matcher. If you're implementing an interface, there's a matcher for that name suffix, and there's a regex type matcher. So the things on the left are all of the Java class names if you want to use this kind of raw from Java. And the things on the right are the Structurizr DSL wrappers and equivalents to those things. So you have a whole bunch of options to identify the primary types of components. And there's an interface that sits on top of all of this stuff, so you could engineer your own strategies if you want to. That's absolutely fine. Supporting types. What is this concept of a supporting type? Imagine we have a pretty standard kind of layered architecture where we've got a controller layer, we've got some sort of like a service layer and some type of a repository layer. The primary types we want to identify here are these. So I want to identify the custom controller, I want to identify the custom service, and I want to identify the customer repository. If I was to take those three red boxes and turn them into a component diagram, we've got two boxes with a link between them and two boxes with a link between them, but there's nothing connecting those two groups of two boxes. In fact, no, we've got three boxes and they're not connected at all. So we've got customer controller to customer service, gap, customer repository. So we need to add more information here because the dependency from the customer service to the customer repository is via the implementation class, not the interface. So that's why there's an additional concept of supporting types. You want to be able to identify the types that support the primary type and essentially act as the implementation details for that component. So what we also want to do here is we want to find those things and add them to the story so that when we reverse engineer the component diagram, we get three components and all the arrows between those three components. So that's the supporting types concept. And again, there's a bunch of stuff built in to do this. And the supporting type strategy you use will depend on your code base. So for the Spring particular example, we didn't need it because we could just rely solely on the primary types as being the identification mechanism. For most code bases, that's not the case. You have an interface and a bunch of implementation classes. So the built-in strategies include looking for all of the referenced types inside a particular package. You could look at all referenced types across your entire code base. These may or may not work depending on how clean or messy your code base is, of course. You could look at all types in the package and all types under the package. Those two strategies are particularly useful for Spring Modulith because Spring Modulith basically says here's your app package and every sub package represents a module. So those strategies can be used to identify Spring Modulith modules. Or you could say go find me implementation classes where the name has a prefix or suffix of whatever it is. So impl is a good example of a suffix strategy. Find me all of the implementation classes that match the interface name with the word impl at the end of them, for example. Some observations. I know this has been a lot for everybody to kind of get their heads around it. We've been on quite a journey here. Some observations. This works really well if you have a well-structured code base. I can't stress that enough. Observation number two, you do need to have an understanding of what you think the component diagram is going to look like when you go through this process. Because you need to curate the rules and the heuristics you use to reverse engineer that. C4 is an abstraction first approach to diagramming, and I think this particularly is very prevalent here. In order to draw a component diagram, you really do need to understand what a component is inside your code base. And it really does force you to think about how to identify components in your code base. That, of course, has an impact on the structure of your code base. So a real world story, I ran the initial version of this tooling over one of my own apps. It was mostly fine, but some of the dependency arrows were backwards. Now, in a tool like Visio, that's easy to fix. You just flip the arrows and you're all good. But that's cheating. So what I did instead was I went back to my code, I found where the dependencies were backwards in my code base, and I flipped the things on its head. Reran the process to reverse engineer the diagram, and my component diagram looked beautiful. It was all nicely organized and all the arrows were going in a single direction, and it was a wonderful moment. The irony of going through this process is that I no longer needed the diagram to navigate my code base, because my code base has been cleaned up by me cleaning up the diagram. So it's a really, really interesting feedback loop that you can go through. And that's that. I hope you found it useful. If you want to look all this stuff up, go to the docs.structurizr.com. I'm going to start writing up all of the documentation about the component finder. Thank you very much.
We have time for questions. Any questions to Simon? Yeah.
Sorry, do you always have to provide the binary, or is it enough to work on the source code?
So do you always need to provide the binary? Yes. So the particular way I've implemented this is that it uses Apache BSL to do all of the identification of types and dependencies. So and that only works off the binaries. So yeah, you do need to provide the binaries, the class files. You can either do that as a directory of class files or as a jar file, as you saw here. And again, you can plug in different ways to get binaries if you need to.
Yeah, how well does it support other types of JVM-based languages like Kotlin, for instance?
How does it support other JVM languages? The honest answer is I don't know, because I don't really use them. I have a feeling this should mostly work, but I would definitely like some feedback on that from people.
So I was curious if you wanted to like expand this to like an organization or just like multiple teams. Have you had some stories about organizations doing that?
So in terms of organizational and enterprise use, yes, I have a bunch of clients of mine and other companies that I know who are using Structurizr across the organization. So they have a single catalog of all of their software systems, and then all of the different teams extend that system catalog and add a detail just for their own software system. And then they push all of those workspaces to a single on-premises install, and then anybody can get all of the diagrams. And if you rename something in the system catalog, it gets renamed across everywhere. And you can automatically generate landscape diagrams of how all systems are collaborating. So yeah, that definitely exists.
I noticed that you couldn't click down from the components to the code level. Could you generate something meaningful at that level as well?
You could do. So in terms of double-clicking a component to show the codes inside it, the Structurizr tooling allows you to insert arbitrary diagrams that are either PNG image files or plant.yml or mermaid. So what you could do is you could write some code to generate you a plant.yml class diagram of every component boundary, add all those into the workspace, and then there's a mechanism to hyperlink components to other diagrams if you want to. So you totally could do that. Is it worth doing? I don't know, because in most good IDEs, you can right-click a package or a folder and just get that on demand. So arguably less useful, but you could do if you want to, yeah.
Thank you, Simon.
Thank you. Thank you.